Okay. So today I'm going to give a talk. I usually don't give a talk on the workshop. At least in the past, 4 or 5 workshops, I have not given a talk. I think being part of organizers obliges me feeling not to give a talk. On this one, I felt it would be okay to give a talk. Maybe I shouldn't have misused my position and privilege as the organizer, but in fact, I have misused it because I'm giving 2 talks. So I'm giving one this week and one next week. So today I'm basically reviewing swampland conditions. And next week I'm going to talk about the more recent work about strings and cosmology in the context of swampland. So about today's talk, we have already heard 2 very nice talks on some aspects of swampland. So it kind of does more or less half of what I want to do. But I will probably try to take a slightly different perspective, even though we had very, very nice talks indeed for the first 2 days on the subject. So I will try to perhaps go to the original motivation and remind you why we were talking about swampland, and then talk about some extra conditions that have not been discussed about the swampland, and with the motivation that bringing up some new ideas maybe adds some particular points there too. Okay, so those are the basic points, and again, as usual, feel free to ask questions. Very informal, and so what is the motivation? So I think that since early days in string theory, we learned about how to construct string compactification. At the beginning, it was a belief that there's only one, or at least in some people, I'm not saying everybody, some people believe that there might be a unique, consistent string theory compactification. Now, you could, of course, look at toroidal compactification or something that doesn't look like our universe. So people hope that, maybe there's exactly one which is actually non-perturbatively consistent. And that was good because we did not know non-perturbative string theory, so it was easy to push it there. We don't know non-perturbative, so maybe that solves the whole problem for us. That was the hope by some people. And some others felt, no, well, we have these choices, that's the way it is. They look okay, but we don't know why we're in a particular one and so forth, so they left it as unknown. And then we discovered string dualities in the mid-90s. And when that happened, that hope that there was this non-perturbative magic, which will throw everything except our universe as the only consistent one, was completely gone. And we had this, no doubt, therefore everybody believed that we have a plethora of possible consistent string vacua. There was no doubt that was the case. So then that people had to live with that fact that we don't still know why we lived in a particular one that we do live, but other ones are perfectly fine as well. Especially the ones with more supersymmetry, the finer they are, kind of. We are more and more sure, the more you have structure there. But our universe does not have, for example, any supersymmetry, and seems to be very interesting, some very special parameters, special structures. So it became very challenging to try to fit exactly how we get ours into this universe. So people began to ask which one is ours. And people had models which look more or less like our universe with 3 generations, more or less, with perhaps a little more here and there particles or fields, or maybe a few more gauge groups and so on, but roughly the standard model gauge groups or some grand unified version. So people were more or less happy with the kind of a structure we had. But we wanted to be more precise and get things right and so forth, and people began to ask more detailed questions until it was discovered. Well, before it was discovered, people were trying to prove why cosmological constant is 0 using string ideas. Okay, well, it was believed at that time it was so small, less than 10 to the minus 120 in fundamental units. So people said, well, come on, it cannot be so small and not 0, so let's understand why it's 0. And luckily, there was no idea in string theory to prove it's 0. So so that was a problem, or if you wish, a prediction. I would turn it around. Our failure to solve the cosmological constant problem was consistent with the fact that it was later discovered to be not 0. Okay, so that was a twisted way of perhaps saying the history, but let's put it that way, positive spin, always. So, okay, so that was, we were happy, but then the value was small. And but in this case, Weinberg's anthropic argument, which predated the discovery, gets the value within the right ballpark. And so people began to think that, oh, well, maybe the idea that Weinberg said was the correct idea. That is, you have a huge number of possible vacua, as string theory gives you, with all these possible cosmological constants. And so therefore, the one which is least fine-tuned with the precondition that we exist, that structure forms, is the one we're going to get. That means the naturalness subject to the condition that we are there to even ask the question, kind of. So that was an anthropic principle applied and getting the right answer. So this inclined the string theory community to take it a bit more seriously, this idea. And so we said, okay, great, we have this huge number of vacua. So that's good for that Weinberg's first precondition, that we need many of them. We know they are fine, non-perturbatively fine. And there's a huge number of them, so therefore pick the one you want. And, well, one of them should be at least, if you have bigger than a certain number, then you can get Cosmological constants sufficiently small, and we are okay. And the ideas of how you might do this, for example, if you have some flux compactifications of some kind, which if you freeze everything, you have some de Sitter vacuum of some sort, and you can tunnel from one to the other with lower and lower cosmological constant until you end up with our universe, like the ones Boussois and Polchinski discussed, for example. So this was a kind of a picture which was emerging, and this idea that you have a huge plethora of possibilities and this solves everything was taking over, basically, that in the community of string theory, that you basically can do anything you want. And then, of course, which one exactly gives you 10 to the minus 122 would be very difficult from this viewpoint. You have to search at least 10 to the 122 vacua to get this idea, and good luck. So people in string theory said, okay, we know that in principle we solve this problem. In practice, who knows? We can't do it. We can't establish it. We at least give general arguments for why these structures exist the way they are, but that's good enough. Once we give general features like our universe, then the rest is just some random thing we ended up here it is, and we don't have to do anything. And so string theory lost its power in some sense. And why did it lose its power? Because the belief was that you can get anything you want. Since they're 10 to 122, you can get anything you want, or close to anything you want, sufficiently close that you don't have to worry about what string theory gives. In other words, the question about string compactification on a manifold, which gives you a four-dimensional physics, since this is huge number of choices, if you include the choices of fluxes and this and that, the belief was, therefore, you get almost all 4D physics, which is at least consistent in the sense of no anomalies or some inconsistency, which is striking. So people said, well, they didn't say it explicitly the way I'm saying it, but that was in the back of their mind. Look, you can write anything you want, and some bored string theorist in the corner will figure it out, perhaps how to get it. I'm not going to waste my time with it. In fact, 10 to the 120 is too many. Let them worry about it. Okay? So string theory became, in a sense, useless because you just say, I write an effective field theory, and who is to say that's not possible to get? If you want to say it's not, prove it. It's not possible to get it. That was kind of the attitude. So people kind of shifted the gear that we are all okay, just write the effective field theory. Thanks to you string theorists, guys. Yes, it exists. It's fine. It's good to know, but we don't need it anymore. We just write our consistent theory. Effective field theory is powerful enough to give us everything. Okay, somebody's getting angry. I don't know. Okay, anyhow, sorry. So, okay. Now, then, so we begin to ask the question, is it true? Is it true that you can get anything you want? And so this is the beginning of questioning of the dogma that anything you want, which looks consistent, goes. So let me try to bring the very concrete example which kind of illustrates what it is. So consider a seven-dimensional physics. So the seven-dimensional physics with let's say half the maximal allowed supersymmetry with 16 supercharges, and you ask what kind of gauge systems can you get in 7 dimensions? Well, we know how to get in different versions of string theory various gauge groups. For example, you can take type 2A and take D6 branes, parallel D6 branes, and stack them up, and you can get a UN gauge group on them if you have n of these parallel ones. So you can get any n. Or you can get take M theory on C2 modded out by a discrete subgroup of SU2. So if you take a discrete subgroup and mod it out, if you take the discrete subgroup to be cyclic acting on C2, a subgroup of SU2, then you get UN gauge group if you take Zn, and if you take more generally arbitrary ADE subgroups of SU2, you get ADE gauge groups. So you can get any at least simply laced gauge groups with no problem in 7 dimensions. So at least if you're trying to construct something on field theory in 7 dimensions, you can get any ADE. So you would say, I will couple this to gravity. You take ADE coupled to gravity, like SU 10,000 or U 10,000, and couple this one to gravity with half the maximal supersymmetry. What is the problem with this? No problem. It's consistent, looks fine. I can have effective field theory. String theory is constructed for me. Can we actually construct this gravity theory? The answer is no. Why? Well, it's not necessarily obvious why no, but we cannot construct it. So constructions we know, for example, involve M theory or type 2A on a compact manifold, versus this was in a field theory setup. So if you want to have gravity dynamical, you need a compact space. So you need, for example, in the context of M theory, you need to compactify this 4 manifold. And 4 manifold with this much supersymmetry in the M theory context means hyperkähler, and there's a unique one, it's K3. So you have to use K3. And so you use K3, and then you say, okay, no problem, I put these singularities inside K3. What's the big deal? Well, the problem is that there's a maximum amount of singularity you can have. The rank cannot be more than, I don't know, something like 22. So therefore, you cannot get any gauge symmetry whose rank is bigger than 22 using string theoretic ideas with this much supersymmetry that we know of. Now, do we have a proof that this cannot be done? No, we don't, because we just have constructions. But it's basically believed that all these duality webs, whenever you have some theory which for other reasons you expect there to exist, there's a way to get them. Here we don't have reasons for this to exist a priori, and therefore we believe this does not exist. As in all of these ideas in the context of Swampland, we never prove it. We cannot prove it because we do not have a definition of string theory. So I don't have even a way to say, okay, all possible things are these and you cannot, because we don't know what's the definition. So we cannot prove it by any means. But it's reasonable to believe you cannot get U 10,000 coupled to gravity. So we say this belongs to Swampland. Now, in all cases, it's not clear why it is. So try to understand and find out what is the physics involved. It's very non-trivial. And this is the hardest task we have in front of us. Understand what are the universality conditions in the quantum theory of gravity which prevent something like these not to exist. But this is a very instructive example because the number of allowed possibilities, allowed ranks, the number of constructible ranks divided to the number of allowed ranks is 0.
Allowed means field theory.
That's right. The number of allowed ranks, meaning the rounds that you can construct in field theory, then you can naively say I couple it to gravity. So the naively consistent ones are infinite. There are infinite ranks allowed, and then there are a finite number here, and finite over infinite is 0. So in this very simple example, the ratio of allowed possibilities, the actual possibilities to what naively looks allowed is 0. So this leads us to think that the string landscape, the ones we can get using quantum gravity, is a measure 0 compared to all possible ones. That's the rough idea. So we basically are in a very isolated special island which allows for the gravity to exist. So that actually changes the whole picture. In other words, it is not possible to go back from 4D physics to M theory because the 4D physics that you end up generally when you have a consistent looking one is typically going to be very, very sparse in some sense. So the space of possibilities is somehow like these discrete points in an otherwise consistent looking space. And it's not that you can get near every point you want. It's not dense. This ADE example shows you, like U 10,000 is not near U anything that we have in gravity. So it is not true that this is dense in any sense. So therefore, we really have isolated islands of beautiful quantum gravity theories. And the general thing, wild thing, Swampland is there, nevertheless. So we have a very interesting task to isolate what is it that picks out these conditions. What is the universality classes? What is the ideas which makes quantum gravities consistent, and what breaks it?
Without appealing to string theory, just in field theory language.
We have to understand in quantum gravity what goes wrong, because string theory, we cannot use string theory by itself, because even if we try to use that, there could be exotic constructions. Nobody has done it yet. So the idea, therefore, is to use string ideas or M-theory constructions to get a handle on some intuition. But that's not a proof. Try to get intuition using black holes or other ideas to try to come up with reasons. Now, these are not going to be easy, because all these ideas, in particular black holes and so on, are not well understood either. So some aspects we understand, some aspects we don't. But generally, that's the basic goal, to try to connect them. Now, the more ideas, the more connections we find, the more we believe these constraints. So in other words, it's going to be accumulation of evidence which will convince us that something is true or not. Yes?
We have a structure which we can construct a huge number of CFTs, which supposedly give you a huge number of quantum theories.
Yes.
And they could be very closely spaced because they're supported by clusters. How should I think about those cases?
Well, first of all, not all the CFTs have ADS duals. That's number one. People have no-go theorems for that. And non-supersymmetric ones will not have a good ADS dual. So therefore, in other words, you will not have a gravity based on it. I will mention that. So it's not going to be like that. But yes, indeed, we have a huge number of supersymmetric ADS CFT pairs. But that I would say is a measure zero. It's not like you cannot get an infinite set. I'm not saying that these points are few. They are few compared to the possibilities, but they are infinite still. So you could have a huge number, but a huger number of possibilities. So compared to what could have been, it's almost nothing. That's all I'm saying. It doesn't say that our task is trivial because there's only one or two. No, I'm not making that statement. Yes?
So suppose we know that supergravity in this dimension with this many supercharges and so on exists. But string theory will tell us that it does not exist for some reason. So these reasons you want to find.
Well, those are exactly like that. So for example, if we had 11-dimensional supergravity and there was no analog to things that we believe comes from string theory, at some point we thought that was the case. We were doubting whether 11-dimensional theory exists or not because we can't get it. We learned that you can get it later by strong coupling of type 2a. So that was kind of a picture like that. And that began to convince us we are not missing anything. We have the correct theory. Whatever that looks consistent, at least magically supergravity existence sounded really magical. That was provided by string theory. But not everything goes. And that is the...
Basically, word supergravity is not enough for us.
Word supergravity is definitely not enough, yes.
So
Yes.
We are looking for other words.
On top of the rank of the gauge group, there is also the Chern-Simons level. Is it also constrained?
Chern-Simons level in the, you mean 7 dimensions?
Yeah.
I don't think there is any particular, even in the context of field theory or gravity?
I mean, in the
Gravity.
on K3.
I don't think, I haven't thought about it. I don't know, I haven't thought about it. So, okay, so, good. So that was the beginning.
I would think it would have to be constrained. I mean, if you start
No.
with a specific K3.
No, it is constrained, but you're not asking if it's infinitely many choices. You're asking what are the choices, right?
Of course, there are infinitely many, but I'm asking which ones can be reached.
No, I know, but there are only finite number of them that you can write. Right. But so I don't. He knows that it's not infinite. So anyhow, so let's talk about the connection of this to geometry. So what does it mean to talk about consistent field theories and consistent gravity theories? What is the difference in string theory? Well, the difference in string theory is the statement of whether you compactify or you don't. So, for example, if you take the D6 branes, you stack them next to each other. What is the problem with compactifying the internal geometry? So, in other words, there are in this case, you go in the type 2a from 10 to 7. There are 3 transverse dimensions. What's wrong with putting them on a 3-dimensional torus? Well, what is wrong if you do this is that you have a problem with charge conservations for the D6 branes, which are points inside that. So you have a flux that has nowhere to go. So you have those kind of problems. So compactification gives you trouble. That's in this language. And in this language, you have a similar issue that you have compactification, which can give you trouble. So it's not like you can do anything you want. You cannot take a non-compact space and compactify it any way you want. That's the lesson from this example. You cannot put arbitrary gamma, which looks perfectly fine mathematically as a non-compact space for large Zn, and hope that there is a compactification. Compactification is a very non-trivial thing. So how you piece them together is non-trivial, and that is the difference geometrically, at least in these geometric constructions, between gravity and non-gravitational theories. So compact means gravity, and non-compact means non-gravitational, no gravity.
Remember discussion during Randall syndrome and so on that we would say that there are no gravitons on the brain, so brain is not gravitational cell.
That's right.
But they would want to get from non-compact things still to get the gravity on the brain. And then there was a discussion of whether it's possible.
Well, the gravity on this case is given proportional to the analog of M Planck is proportional to some power of volume. So therefore, if in the 7-dimensional sense, there is a 10D graviton. We're not talking about that.
Is there, but
not as a 7-dimensional gravity theory. So these are defects. These are defects in a 10-dimensional supergravity, but not in a 7-dimensional quantum gravity.
But this guy somehow got it without.
Who? Which guys?
Randall syndrome.
Well, that was not a string construction. That was just a field theory. Well, I'm talking about things that you can get in string theory. Whether in some limits you can get Randall syndrome is not what I'm discussing now. Okay, good. So this is the difference. So whenever you have a criteria, you could try to translate it between what can happen in a compact manifold and what can't happen in what can happen in compact versus non-compact, and that could give you a criteria between what we can call effective field theory versus quantum gravity. So that's a rough guide. Okay, so now I start trying to enumerate a few of these conditions. So these are some of the ones we already heard about, so I'll be very brief. The first one was no global symmetries. So these were beautifully discussed in the last two lectures. We don't have a full reason why it is. Black holes are closest to coming to an explanation of this fact. So that's one thing that one has to keep in mind. In fact, black holes should play some kind. It's natural that the black holes play some kind of role because 2D quantum gravity can have global symmetries. So it's not true that in any dimension the quantum gravity has problem with global symmetries. And 2D, the black hole story is not the usual story. So those who wonder what is the 2D quantum gravity coupled to gravity, why it could have global symmetries, can remember string theory can have global symmetries on the worksheet. And we sum over the worksheets. So from the 2D perspective, there's no problem with having global symmetries. So this fact is non-trivial in higher dimensions. In 2 dimensions, it's not even true. But we can start with higher dimensions, as we were talking about. 2 dimension always or very often ends up being the odd case out in some of these conditions. So we're not talking necessarily about 2D cases. Now, so there are arguments for them, but the black hole arguments for higher dimensions were useful for the case where you have continuous global symmetries. Discrete ones, you cannot use that argument. It would be nice to come up with an argument which covers the discrete case. In the context of ADS CFT, so supersymmetric ones, Harlow and Uguri have an argument that I hope perhaps Hiroshi will describe it here in the workshop later. But we don't have a general argument even for that case. Why, for general theories, we don't have these symmetries. It would be nice to come up with an argument, even if it's heuristic. Why is it that gravity cannot have global symmetries? This is counter to a lot of things we know in physics. Symmetric things are supposed to be easier and nicer. This is saying, no, just break it a little bit, you're fine. But don't go to the symmetric points. It's a very strange phenomena in the quantum gravity. So not only effective field theory is wrong in this case, the intuition is totally wrong. It tells you symmetric points are the worst points to be at. You can't rule it out. It's kind of the exact opposite to what you might think is the best point to be at. So that's so much for the intuition for the effective field theories, as symmetries being nice. Okay, now what is the gravity version of these questions? Well, The gravity version of these questions are very easy to understand from the viewpoint of geometric version of understanding between compact versus non-compact. So a compact manifold, for it to have a symmetry from the lower dimension perspective, you have to have some symmetry. Symmetry of internal geometries are isometries, but isometries are part of the diffeomorphism group, which is gauged by gravity. So anything which is left over of those isometries are gauged by definition. We're talking about quantum gravity. Okay, so that's kind of a very... if you don't start with a global symmetry, which in string theory we don't start, you'll never get it, because gravity is kind of already... gravity is already gauging everything else outside.
But, I mean, you can distinguish compact manifolds with isometries and without.
I know. I'm just saying that there are theories...
That's a diffeomorphism invariant state.
No, I'm saying that... I didn't explain perhaps clearly. I'm saying that if you don't have isometries, you don't have any symmetries. So I'm saying consider cases, if you want to talk about symmetries, let's consider cases where we do have isometries. The question is whether it's a global symmetry or a gauge symmetry. So when I say there's no global symmetry, I mean any symmetry. In other words, if there are symmetries, so said differently, if there is symmetry, it must be gauged. That's what I'm trying to say. In this case, it's gauged by diffeomorphism. Or you start with the gauge symmetry and begin with, like in heterotic strings.
What you really mean is that there's no Higgs, there's no Goldstone mode associated with isometries.
For discrete, you don't have.
Well, the discrete one, even, I'm trying to talk about both continuous and discrete. So the general statement is that these isometries are always gauged.
Until you break diffeomorphic symmetry by choosing boundary conditions or something.
Well, you can say you break the gauge symmetry too, Higgs it.
So that's another
You can do that, yeah. That's the same statement.
Right.
Okay, so, and of course we have examples of both continuous and global symmetries, like if you have a circle compactification, the U1 isometry gives you the usual Kaluza-Klein mechanism of giving a U1 gauge symmetry. Or if you have a torus with a Z4 symmetry, you get a discrete Z4 symmetry, for example. So you can arrange to get discrete as well as continuous gauge symmetries in this way, but not global symmetries. Okay, good. That was the first criteria. And then the next criteria was that all the spectrum, all charges of a given gauge group appear. The spectrum is complete, as was discussed in the talks yesterday and before.
Can I ask a very naive question?
Yes?
For discrete symmetry, what's the difference between global and gauge?
So what that means, good question. So what that means is that if you have, for example, a geometry like a circle, you cannot fix the holonomy. You have to sum over all the holonomies. That's a concrete version of saying what's the difference. You sum over all of them. Okay. This has been discussed, and if you have a complete spectrum, and as was discussed, it is believed that these two conditions, the first condition will give you the second condition. It would be good to actually prove that, especially for discrete isometries. Discrete, by that I mean non-abelian isometries and so on. So there were some arguments that you can try to show that this is true. There was a discussion. I guess Tom suggested it, and Matt mentioned in his talk and so forth. It would be good to actually make that to a proof that they follow from one another, at least for the non-abelian case as well.
When you talk about complete spectrum, at least in the non-abelian
Complete
case,
spectrum.
Complete spectrum.
Yes.
In the non-abelian case, some of it seems to be a little bit semantic, right? The complete spectrum of SO3 and the complete spectrum of SU2 are different. I mean, but you say they would be complete spectra.
No, the gauge group.
One will have more monopoles. So
Yes. It's true that it's true that a given Lie algebra is not enough to state the gauge symmetry. That's true. You fix the full group, and then you have compatible with the group you have representation.
But we know, I mean, we have, like, in the heterotic SO spin 32, right, that you can have projections that
That's
remove
right.
certain parts
That's
of the
right.
spectrum, but you don't say it's not complete. Right?
No, I would say it's complete for the group, not spin 32, but spin 32 mod Z2.
Z2, right.
So you have to specify your group carefully. That's correct. So for a given group, you have a complete spectrum.
But the group may be modded out by.
Well, the group is whatever it is. Yes. Okay. Now, what is the geometric analog of the statement that the spectrum is complete? Well, again, we can give examples, like if you take a compact manifolds. So the cycles, homology cycles, integral homology cycles, are typically where you will get these charges. And you take branes and wrap around them, and you get typically all these charges because you can take brane wrapped around any cycle. There's nothing that prevents you from doing it. Okay, so that's the version of doing it. You can see. Now, just bear in mind, it doesn't mean that they're always nice and supersymmetric, even in supersymmetric examples. So, for example, if you take K3, there are cycles in K3 that cannot be occupied by supersymmetric objects. So there's some misunderstanding that people think that in supersymmetry any cycle can be occupied by supersymmetric one. K3 is a beautiful counterexample. If the self-intersection of a cycle is less than -2, it cannot be. It cannot be given by any curve class. It's not a BPS state occupying it. So that's already an interesting place to study. Namely, you can study issues having to do with charge which are not BPS, which are breaking supersymmetry in the context of a supersymmetric system, and that would be one of the things that one should study perhaps more, which hasn't been studied enough in my opinion.
Actually, already in 10 dimensions, right? We can have 10-dimensional super-Young-Mills theory, which will be not possible to couple to gravity.
That's right.
Unless you bring the B field, unless you bring all these.
Well, there's anomalies. In the case of 10D, anomaly restricts it quite a bit, of course.
And it turns out that it's all.
That's right. So you can get anomalies, you can get all, and string theory gives you all, or so therefore we are happy. So people have begun talking about going to 9 and 8. There are some beginning to give some restrictions, but it's not complete, and people are beginning to go one by one down. It's still far from getting a understanding. But we believe the rank is not too big, generally, when you go down.
But the rank is actually in 10 dimensions.
Right. Now, it is. So what about what I told you about the compact case? You could say, what about the non-compact case? Well, non-compact case can have non-compact cycles, so it doesn't mean that you can have necessarily occupied. For example, if you have a U1 gauge theory, for example, like in conifold, you have a 3-sphere. You can wrap around a cycle around it to get the charge electric one, and the magnetic version of it will be something which wraps around the non-compact cycle. And that's infinite mass. So that means it's not part of the effective field theory. So in the non-compact situation, you don't have to occupy everything, and that's a simple counterexample there. So again, the distinction between compact and non-compact is nice to keep in mind in terms of these completeness of spectrum. So you kill some spectrum out by these going to this non-compact limit, making it infinitely massive in that limit. Okay, so that's just an example. So that was the second condition. So I didn't just write 2, complete spectrum. So, and there's a relation between them. It would be interesting to make it more precise. Okay, the third one. So this third one is a universal bound on the number of massless fields. Now, just to make it precise, let me talk about supersymmetric case, just to restrict it to that. And let me talk about even zero cosmological constant, just so that we have a very specific class. Though probably this is more general than that. So how do we get these? Well, there are very natural ways like Calabi-Yau compactifications or G2 or something like that. So the number of massless particles get related to some homology count of the manifold in some homology class. And, well, you might imagine that you can get arbitrarily big numbers, but we don't know if there's a counterexample, but we believe, for example, Calabi-Yau list is finite, the types, as far as the cohomology numbers and so on go. This is, I don't know, Reed's conjecture, or whoever made this conjecture first, I don't know. Yau made the conjecture. Okay, Yau's conjecture, and Reed had the program how you can connect different Calabi-Yaus to one object. And so basically the idea that these could be finite is related to this idea. It is highly non-trivial, this statement, and when I say it's a bound, of course, in a given theory, you have finite number of particles. So what I mean is a universal, uniform bound, independent of the theory. That is, you fix your dimension, you fix the supersymmetry, let's say, and the statement is that you cannot get more than X number of massless scalars in that particular class. That's the statement, more precise statement. Uniform bound. Now, why should there such a thing be true? Well, people have issues. Again, black hole issues come to some kind of a discussion, and the species problem. If you take a species and you have a huge number of them, then you get issues having to do the black hole entropy getting too big. But these are arguments which are kind of indirect and not complete. It'd be nice to see if there's a more precise version of these from gravity side that one can say. Of course, from field theory, there's no problem with taking, there's no bound, obviously. Take SUN gauge group with n goes to infinity, that's perfectly fine. So you can get arbitrary number of massless modes with no problem. So this shows that this is at best a gravity restriction. The fourth one is that there are no free parameters in the quantum gravity. Now, yes? Okay, good question. So here, well, I should clarify. When I say quantum gravity, I mean everything I'm going to talk about is regular quantum gravity. So by that I mean finite number of one graviton and no higher spin, massless fields, and so on. So I'm talking about the regular, what we usually view as Einstein's theory. So anyhow, so in other words, the number of massless fields for me is always finite in my discussion.
Exactly.
Yeah, I'm talking about massless fields which are finite. Right. And the symmetries are the symmetries of the Einstein theory, not the higher spin symmetry. So I'm talking really just about diffeomorphism, gauging diffeomorphism. So there are no free parameters in a quantum gravity. Of course, in regular theory, coupling constants appear as free parameters. So there are free parameters in quantum field theory, but in gravity there are none. Now, what do I mean by that? It doesn't mean that there are no parameters that might appear in an effective theory in 4D. But what that means is that those parameters must be expectation value of some fields. Like axion is the expectation value of it gives you theta angle. So we believe that every parameter that appears in your Lagrangian should be promoted to a field. And it is promoted to a field in string theory. It could have huge mass, Planckian mass perhaps, but they are always vev of some field. Could be frozen, it could be massless, but they're always vevs. There's no, in other words, that what that means is that dynamically you can change that value in a certain region of space. You can change the theta angle by just taking that field and exciting it with sufficient energy. That's what it means to have dynamic, every parameter, no parameter is free. So in the quantum gravity, you should be able to excite every parameter, change every parameter you want with sufficient amount of energy. So there's no free parameter in this theory of quantum gravity. And we don't have a proof why. For example, type 2 strings, or strings in general, have a coupling constant, and you might have thought that this is a free parameter, but we learned from old days in string theory that itself is an expectation value of a scalar field, which is dynamical in that theory. Or M theory in 11 dimension has no free parameters. That's another example it could have had. Geometrically, what these free parameters means, these are typically when you compactify the geometry, you have some moduli or some shapes and so on, and you might put fluxes to freeze them, but there are parameters which is controlling them, and even if you have frozen them at infrared, you can always excite them by going sufficiently high energy. So there's no free parameter. You can go from one to the other with sufficient energy. Nothing is frozen in this with sufficient energy.
So what fixes them actually? When you pick up a ground?
Fluxes. Fluxes, for example. Okay. Good. Somebody has to show me a watch somewhere because I have no idea how I'm doing.
11:42.
Okay, good. 11:42. Okay.
Halfway.
Just one question. So there are type of parameters which are not fixed in field theories, like instanton number, for example. Take Young-Mills, instanton number is not fixed, but it is something that characterizes a configuration. So would you say that this...
That's not, you sum over all of them. They're sectors, you mean. They're subsectors, yes.
But in a theory, it's not fixed. When they give you a theory, it's instanton number. When it's not calculated...
You sum over them.
You sum over
Yeah,
them?
yeah.
So now let's go to the coupling constant.
Yes.
It's the coupling constant.
Yes.
It's not like that, right?
It's a field. It's a vev. It has a vev of a field.
Fine. I would say that instanton number also in some sense is...
No, you have an expectation value of a field. Incident number of a field theory is similar in the sense that you have to sum over them. So it's dynamical. The field is dynamical. In that sense, that's similar. Yes, but the coupling constants of n equals to 4 Yang-Mills is not dynamical in the gauge theory.
No, that's what I meant instanton numbers.
No, I'm trying to give that example. I know what you meant. But just consider that, just to give you the difference, tau is not dynamical.
Yeah.
But in string theory, tau is dynamical.
So in string theory, tau is like instanton number in
Yeah,
theory.
that's right. You sum over there.
That's the whole point.
Yeah. Okay.
You have one parameter, which is the Planck scale.
Well, but the dimension.
That's just takes the scale. That's not. I wouldn't say that.
It's a free parameter.
I wouldn't say it's a free parameter. I would say that defines your scale. That defines your theory. That defines what you mean.
It's something that you fix by.
There are no two M theories with different Planck scales.
You don't fix it. It's a matter of choice.
I can choose it to say that it's a parameter, but okay, it's the second is the cosmological constant.
Any theory, for example, let me just talk about. For example, in the ADS CFD context, you have parameters that you set the value of the energy, and the minimum value is given by a radius. You can change it. So, for example, in ADS CFD correspondence, you have a minimum of a potential at some negative value, and you can move it. It's a web of a field, the radius field in that case. So you can change it. So there's nothing frozen in string theory, forever. In other words, for low energy, yes, but not for arbitrary high energy. It's a beautiful fact, I think. That means that gravity is fluid. That is, you cannot rigidify it completely. You can rigidify it at some limit, but sufficiently high energy, everything melts together. You cannot freeze it. That's, I think, a very interesting feature of gravity. Now, why is it like this? Why is it like this? I don't know. Why should it be like this? Why? For that one, I have no argument. In other words, I don't even have a heuristic argument. Why, in a quantum theory of gravity, there could not be... Why couldn't, for example, M theory have some extra parameters analog of the fine structure constant somewhere? Why not? So, sorry?
You mean only continuous parameters?
Well, continuous for sure, but I would say any parameter.
How do you change the number of generations or the number of dimensions?
You change the topology of the manifold. How do you do that? In a given region, you change that Calabi-Yau, squeeze it and tear it. You can do that. In a finite region in space, you can do anything you want. You can do anything you want. That's the statement. The statement is that the string vacuum will be connected if you go to sufficiently high energy. All the energy with all supersymmetry, you can connect them. You can go anywhere you want with sufficient high energy. That's the basic picture. You can change the dimensions we know by dualities, right? So you take circle, you push it down, you go type 2. The fact that we have a duality web already is, in some sense, if you had disconnected pieces that had no way to get together, that would have been a problem, potentially. So this is the connectivity of the web is a result of this conjecture. Yes?
One question bothered me during these 3 days, which is normally we classify, let's say, operators by anomalous dimensions, or we say that this is the marginal, not marginal, and so on. There is no global group, right? How global group, for example, also will include the notion of dimension, right? Dimension of operator. How do we classify?
We don't classify. No. We can't classify.
We can't say that we have a theory with operator.
No local operator.
No.
So there are no local operators by default, right? By default, there are no local operators.
Yes. Gravity, there are some non-locality in gravity for sure.
Then the next question would be, so how we distinguish? What are the notion that replaces the notion of the local operator?
Well,
Any
I'm not trying to define quantum gravity for you and how it is. There are a huge number of issues about trying to define a Hilbert space for gravity. What does it mean, and what are the good operators? So that's not my I have not thought about this enough to say anything really new or interesting. So I'd rather not venture into that. But that's orthogonal to my questions here. So no free parameters. That was the fourth one. Fifth one, the moduli space. Okay, so suppose you have a space of vacua.
This includes both geometrical and non-geometrical spaces?
The statement is true for all. I'm not saying that one has proven it for all. Yes, the statement, the belief is for all. As I said, we will never be able to prove a single statement I'm making because we don't know the full definition of string theory. So don't even try to say if it's true for all. I don't know what is all. I'm not at that position. But I think there's enough evidence. I think in physics especially in string theory, we have learned to believe in things by examples, like dualities. It was very hard to believe, but after a few checks here and there, which were miraculous, we began to gain confidence. So I think these things we have to gain. It's harder to get confidence because they're a little bit more. How can I say? It's harder to kind of localize them, but we have to try to kind of connect it to principles that we believe, like black hole, unitarity, this and that, to try to make sense out of them.
So changing these three parameters in a region of space, do you run into troubles with everything collapsing in a black hole? So is there a limit on how big this region of space can be?
That's a good question. In other words, what equivalent question would be whether or not these states have to have masses, sub-Planckian masses, basically. That's the question. So one could try to refine the statement is that, no, and that's a good question, whether or not the masses that are involved are always sub-Planckian. So for example, can we show that the axion mass is always less than m Planck? Okay, that would be a question. I don't know. We can refine the statement here, potentially. I don't know if it's true or not, but anyhow. So, okay, so the statement number 5. By the way, I'm not giving the references here as Gary did such a nice thing. He wrote the name of all the collaborators. I wish I had done something like that. But anyhow, I have many collaborators, and many of them are not my work anyhow. So just ignore that aspect. So I'm not going to give any references for today. So I apologize. So the moduli space. Consider a theory which has some parameters. So you have some scalar fields with zero potential, and that's what I mean by moduli. Exactly zero, let's say for now. So you have, and this happens, for example, in supersymmetric theories. So then, again, as was discussed yesterday, so there's a space here. This space, if you start with any point on this space, by the point I mean the web of phi's, specifying your particular point. The kinetic term of this theory gives you a metric on the field space by this definition. So this space, which is called the marginalized space, comes equipped with some metric, which is this metric, which you can read off. The first statement is that this space is not compact. For example, it's not a nice round sphere or something like that, which means that, in particular, means that from every point, if you ask if there is any point sufficiently far away, there are points which are, there exist points. So there exist points like P such that this can be bigger than any number you want. So you choose your distance and you can go farther and farther away.
Is complete Riemannian manifold?
No, there are singularities and all that stuff in this. So you will hit singularities. So what do you want to do with that? There will be singularities in this space. So I'm not dealing with the singularities of it, but there will be directions where you can go to infinity. I'm not saying take a geodesic or anything. I'm just saying there are points which are infinitely far away.
The fact that it's actually Riemannian manifold is obvious. Right?
Well, modulo the question here, there are singularities, of course. So generically it should be Riemannian.
With metric.
But there could be singularities in the metric and all that. Okay, now,
What is the justification?
what is the justification? Good question. There's no justification I know of. It's just, we don't have a counterexample in string theory.
Well, it's based on the fact that there is effective theory has a Lagrangian. And if it has a Lagrangian, then it has a kinetic term.
No. He's asking compactness. So you could have the sigma model.
Why isn't the moduli space?
No obvious reason to me. I don't have. This is one of those things I don't have any obvious explanation. If somebody knows, share it. Or write a paper, brother. I don't have any explanation. This is just observation. It just happens. But if it were compact, I will tell you some bizarre things would have happened. There would be no dualities there, and as will become clear why. So the fact that it's non-compact opens the door for dualities. That's related to the dualities. So what's an example? Compactify the theory on a circle. So suppose you have some theory in d dimension, go one lower dimension by theory on a circle, and then you have give an extra moduli, and if you have supersymmetry or something like that, you will get some kind of there's no problem. We can go down in circle, and you can find in the correct if you write r as e to the lambda or e to the phi, then you find the action looks like d phi. So in this metric, the metric is flat. And it's infinite distance in this language because phi can go from, let's say, 0 to infinity or minus infinity. So the space is infinitely big. Radius can go all the way from 0 to infinity. Okay. Now, you might say, wait, this is what is so special about this? You could imagine field theories are always also like this. If you have some scalar fields, you would usually have what restricts to field theories. This is not true. Field theories can have compact range. I mean, so there are various versions, but an exotic version that I like is little strings in 6 dimensions with 1,0 symmetry. Then you can have ranges of these scalar fields, which are these compact moduli of the spheres. They can form bounded regions of some kind. So there are in field theory you could have a restriction, but in the gravity case you don't. So it could be compact. Okay. Of course, there are other simpler examples, like when you have some kind of symmetry breaking, you get a compact sigma model on a compact manifold. That's another version of this. If you have a potential on the manifold of lowest energy, that's the less exotic example we get. You get sigma model, effective sigma model on some compact space, no problem. Field theory has no problem with that.
Are you saying the modular space has to be non-compact?
Yes. I'm saying that we have observed it, so this is a conjecture, of course.
But has to be non-compact means you can't have any compact submanifolds, or are you allowed to have?
Well, there could be various refinements of the statement, and I'm not making that. But it would be interesting to study further what are the restrictions. But, for example, could you have a sphere in it?
An holomorphic one or a generic even possible? I mean, you
Metric. So yeah, Cumrun's example.
He's talking about topology, probably. He's interested in
That's right.
like a compact sphere with.
Compact sphere or a compact Riemann circle sitting inside of the modular.
You can just take a point, take a sphere of the point of the distance.
Non-trivial homology, he means probably.
Yeah, non-trivial homology.
Anyhow, see, these are interesting questions. I mean, I don't have an answer. To be interesting. So, yes. Good question. So yes, I'm here assuming that this like an M theory. So here, there's a counterexample to what I just said, which is M theory. You could say there's no field, but here I'm talking about field when you have actually a field space.
By one, different from zero.
So, sorry, you were. This is the response to this question? Yes, I
But
did.
in n equal to 2, you can show that only pi 1 is different from 0 and higher pi is 3.
Okay. Okay.
You need supersymmetry.
For supersymmetric ones, so he believes at least it's true for. Well, typically this we believe it's only in supersymmetric ones anyhow. So in some sense, it's okay even to restrict to supersymmetric case for this question.
This is the analog of just the statement that if you always, in all examples we know, you always have either Taylor modulus or complex structure, which can go to infinity.
Well,
You can go to infinity. That's right. That's right. That's right.
Special global properties of special geometry.
And then there's this distance conjecture. There was a discussion whether we should call it Swampland distance conjecture or distance conjecture. I don't know, whatever people feel they can talk about. But then, yeah, let me just call it distance conjecture because all of these conjectures are Swampland conjectures. So it would be funny, Swampland 1, Swampland 2. There are refinements of this actually, which I think Aaron, you're going to talk about, right? Yes. So there's going to be refinements, and I think in his paper he called this distance conjecture or refined distance conjecture. Oh, you're not talking about that? No, I'm talking about it now, right now. So what I'm going to be talking about. So there's the statement that if you go as the distance goes to infinity, if you go farther and farther away, as was discussed, you get a tower of mass states which go like e to the minus d times some constant, where the constants of order 1 in Planck units, but and the distance is d, and we're doing everything in Planck units. And the motivations for this was discussed, but let me add one motivation for this. If you start with this, you can almost prove that theory of quantum gravity must have extended objects. In other words, instead of saying I start with string theory or membrane theory or whatnot, just with this assumption that you get tower of light states, you can prove there must be extended objects in that theory. That's remarkable. That's, in other words, you can reverse the order. You don't start with string theory and get this as constant, because you can actually, there must be some extended objects. How does that go? Well, it's a little heuristic, but let me explain the idea. You start from some theory in d dimension, and you go to d minus 1 on a circle of a radius r. So you write the radius r as e to the lambda, or e to the phi, and the theory is d phi, d phi. And we said that if you had phi equal to 0, you can go to phi equals to infinity, and that corresponds to radius going to infinity. And indeed, as the distance goes to infinity, you get light KK modes. That's good. That's consistent. But there's another direction you could go, this way. So you can shrink it further and further. The KK mode becomes heavier and heavier. And if your theory did not include extended objects, there's no reason you get light states. Okay? In other words, you get heavier and heavier stuff, and therefore, this will be a contradiction with this statement, that if you go farther enough, you should get light state. So what happens in string theory or M theory, you get wrapped strings or wrapped membranes around the circle, which are extended, which feels the global topology of a circle. So you need some object which is not local for this to happen, at the very least, in some form, and that's naturally in the context of extended object. This is not a strict proof, but it gives you an idea. Why is it not a strict proof? Well, you could have a situation where the radius, there's a potential as a function of r, for example. So I cannot exclude that possibility. You might be restricted to some finite range in r. But for supersymmetric ones, at least, it will be kind of an argument. So at any rate, as long as you can argue that there's no potential generated in that particular supersymmetric case, it's a kind of an argument.
Dimensional reduction are not possible.
Sorry?
Actually, when you go to infinite distances, typically it's not true that things become light. Actually, things become extremely heavy.
KK modes become heavy.
So, like for example, just decompact phi type 2a. Then deep waves are all backward cycles, and all cycles are getting to infinite size.
So which example do you have to talk? Which circle are you talking?
Take type 2a.
On a circle.
No, on a Calabi-Al or whatever you want.
What's the angle of the circle we're talking about? I'm talking about the circle. I'm taking your theory, putting it on a circle, and I'm just talking about the radius of the circle going to 0.
I'm just saying that this m going like e to minus dA, that what it is m over m Planck goes like e to minus dA.
Yeah.
And when you, yes, I don't know if the question here is, because it doesn't mean, for example, I'm saying type 2a, you take type 2a, yeah, but if you take type 2a and you decompact it by, that makes all become more massive, everything becomes more and more massive.
Okay, we can talk about it. But at any rate, this is giving you an idea that we can, by rephrasing these kind of conditions, we might be able to get an insight about what string theory is. That quantum gravity must necessarily include extended objects is related to this. In fact, this conjecture is basically related to understanding dualities. Namely, at far enough distance, when the light tower appears, there must be a dual description. The existence of this light tower is exactly the smoking gun for a dual frame of reference of understanding that theory. So this is the bread and butter of duality. So this statement includes beginning of understanding of duality as well as understanding of extended object necessity for that. So this statement is quite powerful, actually.
Where does this this argument he used, the theory was a theory of gravity and not just.
There's no argument here. This is just a conjecture. So I didn't give you any argument. You start with statements and you can check.
Consistent, different behavior.
No, I meant that if I take just field theory, no gravity, nothing, just field theory,
Then this is not true in field theory, of course.
not true.
Yes.
So somewhere in this argument,
Gravity should come in.
and
In
I
all
try to
of
understand
these,
where it is.
in all of these, gravity should come in somewhere, and I'm not claiming I know where. Some of them we have heuristics where, none of them we have exactly why where. So those are exactly the kind of things we need to be better at. That's exactly the kind of things I wish I knew better answers to. What time is it now?
12:04.
Okay, good. So we are running on time. Good. Okay, so there are 10 conjectures. I guess we're getting there, right? So it's about right. So 6 is done. So we are moving to 7. Well, this conjecture is a little funny. I'm going to say it. I was actually not quite sure I should say it or not. It's kind of, yeah. So these moduli space of these scalars I talked about, when you have flat potential, is typically in the form some contractible space we call Teichmuller space with some group action acting on it. This is a typical geometry of them. And these groups are generated. This group is generated by some elements typically of finite order. So you typically have some finite order elements which generate. Sorry?
This is not typically n equal to 2.
This is not typical n equal to 2.
Take,
No, you're talking about cone of field theory or cone of gravity.
well, yeah, we take the mirror quintic is not generated by...
Really?
Yeah.
It's not finite, you mean?
You have finitely many generators, but they are not finite order.
Okay. Okay, so anyhow, they're finite. So maybe I'm not sure which example we should talk about afterwards. But they're finite generators for these elements. And the question is, like SL2Z, like S and ST, you can view it as order 2 and order 3 elements. And the question is, what can we say about this space? Well, this is a conjecture which is related to the fundamental group of it. Question is, what is the fundamental group of this space? So we don't know a priori what it is. It could be non-trivial or trivial. But in at least examples I know, maybe Sergio knows better, that they are trivial. The fundamental group is trivial. And in this way, you can always contract any loop you have in the moduli space to nothing. Do you have a counterexample?
No, it is in the footnote of your
Yes. Yes.
that you have moduli which are C star.
Moduli which are C star.
Yes, the sphere with less 2 points. And that is, for example...
Which Calabi are we talking about?
The mirror of the quintic is just like that.
No. The C star, for example, the moduli space, one point is the Landau-Ginzburg point. It's not C star. It's C. It's a C star, but it's actually there's a point. There's one point of infinity only. The one point is finite distance. So there's not the Landau-Ginzburg point is not that. The R goes. You're talking about R goes to minus infinity. Well, we can talk about that. Maybe there's a misunderstanding. But the point here is that if you had a non-trivial cycle, you can actually try to create a global charge out of it. Namely, you can, suppose you have a non-trivial charge. A good example of this is the axion. Theta goes to theta plus 2 pi. So you could say, well, there's a non-trivial circle in the axion. What's the problem with that? Well, the problem with that in the context of all these axionic things is that you can contract this guy using the fixed points that you have for the action near the third and the fourth roots of unity. In particular, the SL2Z here is generated by S and ST transformations, and the product of them gives you the T transformation, which is the axion shift that you're talking about. And these two fixed points, which are here and here, these finite order elements involve having fixed points, and you can contract this by getting close to these guys and breaking it up to fixed points like that. So whether this is true or not, I don't know, but one possible explanation would be if this was non-contractible, you could consider the theory on a circle and wrap around this circle and gives you a winding number, which is not gauged. So you get a global symmetry out of it, and you're not supposed to get global symmetries. So having a fundamental group is not good for global symmetries. Yes?
Do you really mean the fundamental group or not H1?
Sorry?
Do you really mean I1 and not H1?
I mean pi 1. Well, pi 1 forms the, well, pi 1 is stronger statement, clearly, right?
Yeah, but any loop is contractible baseline. Because pi 1 involves fixed baseline.
Anything is contractible in pi 1? Yeah, but then I'm talking about pi 1 here. Yeah, it's a stronger statement. Okay, let me move on to the weak gravity conjecture. This is the 8th one. So again, this was covered beautifully yesterday and the day before, so I won't talk too much about it. The motivation again is black holes. Let me just say that the version that the most I mean, there are these other versions that would potentially true, but the most conservative version is that there is one object. This is the most conservative one. There's one object whose mass is less than m Planck, whose mass is less than q. That would be the least, I think, least strong version of it, which is I would say is the benchmark kind of. Now, why do we believe in this weak gravity conjecture? Well, there are examples, and I think the most interesting example, in my opinion, is the heterotic string example, which is dual to the K3 I just told you about. So there are these non-supersymmetric cycles in K3, whose self-intersection is less than -2, and in the duality between heterotic string on T4 and type 2 on K3, they get mapped to certain states in heterotic strings, and the heterotic string states have a structure whose mass goes like 1/2 m squared, is 1/2 p squared minus 1 in string units. And in this case, you see that m is less than p. Because of this tachyon shift in the ground state of the heterotic string. Because of that -1, you get this inequality. And this is an example, very, very interesting example of this weak gravity conjecture, which is, I mean, if there was a +1, it would not have worked. It would have been counterexample, but it does work this way. Anyhow, it would be interesting to give more examples, and in particular, I think it would be interesting to study K3. This would suggest that if you study non-supersymmetric cycles, minimal but non-supersymmetric holomorphic cycles in K3, they should have similar bounds. The area should be less than the corresponding charge. And this has not been shown mathematically. So I think it would be interesting to show that the dual picture is not known. And it doesn't follow by string dualities because it's not BPS object. You cannot use BPS to argue it. So you have to study it in its own right. So it'd be a very interesting question to study.
You use the word holomorphic. So it's supposed to be, I mean, there aren't holomorphic cycles with this self-intersection.
There's what?
There are no holomorphic cycles.
Yes. That's why they cannot be supersymmetric. That's what I was saying. So minimal. So there are minimal. There are no. You look at minimal. You take a class. You look at minimal area cycles in that class. That exists presumably, and then you could break up to pieces. But then yeah, you can talk about the minimal area in that class, even if it's degenerate, and that's what I'm talking about. There's a sharpened version of the weak gravity conjecture, which was also mentioned, which is m is less than or equal to q. M is less than q for non-SUSY case, and the equality sign only appears for SUSY case. By that I mean the theory should be supersymmetric, and the object we're talking about should be the BPS objects. So that's a sharpened version of the weak gravity conjecture. Of course, these extend not just to strings, not just to particles, but also strings, membranes, etc., to higher dimension, as well as lower dimensional objects, like it was discussed yesterday in the context of axions. So you can talk, it's a whole range of conjectures. I'm talking only in the particle language. And the sharpened version of the weak gravity conjecture, which is m is less than q, suggests that ADS CFT holography for non-supersymmetric case will not work the way it works for the supersymmetric case. And the reason is, in the case of the supersymmetric case, we put parallel branes, and the gravity force attraction exactly balances repulsion. If the mass is less than the charge, as the refined conjecture, sharpened conjecture of the weak gravity conjecture goes, the repulsion force wins over the gravitational attraction. You cannot put parallel branes in a non-supersymmetric setup. You cannot form ADS CFT in the usual way we know in a non-supersymmetric case. So this suggests perhaps the non-supersymmetric ADS is not stable. It suggests that, and that would be a kind of not a follow-up, but a kind of a a sharpened version of this conjecture, I guess I will give it a number 9, let's say. So non-SUSY de Sitter is not ADS is not stable. Now let's make clear what this means. This means that if you have a regular gravity with a regular things, not infinitely many light states and all that, then presumably there's no analog of the holography in that context. This does not mean that non-supersymmetric holography cannot happen in any sense. In some sense, it should happen, and it does happen. For example, in the SYK models, you have non-supersymmetric theories, and there's an ADS dual. But in that context, you have actually infinitely many modes. So it's not you have a gravity with a gap. So the statement is that you cannot have a theory with a gap, sufficiently big gap, parametrically big gap, which these theories would demand. Now, you might think this sounds a bit exotic. For example, you take let me just give you an example of how this works. Take ADS3 times S3 times K3. So we know with the fluxes and all that, this is a perfectly fine geometry, and it's nicely holographic to symmetric product of K3s, sigma models under this space. So that's perfectly fine, but this is supersymmetric. Now you say, okay, what is the big deal? You can take the non-supersymmetric version. What does non-supersymmetric version mean? Well, just to make the life simpler, let's do the version which this is T4 and replace this by T4. So take the symmetric products of T4 without supersymmetry. That you can also do. You can take T4 with no fermions, sigma model. Take the symmetric product, no problem with that. So what's the problem? You will get this the right-hand side for sure makes sense. The right-hand side for sure makes sense. So what's the problem of trying to define a gravity theory using the conformal theory? The problem is this. In the context of supersymmetric one, to actually get a finite geometry, to have an ADS 3 times S3, which is not singular, you need to turn on a mode. Which mode is this? Well, symmetric products of T4 involves points where the manifold comes together, and it's singular. You have to give a vev to that field. And you give a vev to that field, and then you get a dual description. In the limit that's shrunk to 0, you get a singular situation. You have infinitely many modes and all that. The holography would not work nicely in that limit. If you want to get the regular gravity with modes which are gapped and so on, you need to do this. Well, you say, okay, I'll do the same thing in the bosonic case. Not so fast. When you take the symmetric points, there's no marginal operator. You lose your marginal operator when the two T4s come together. So it's the fact that there's a marginal operator corresponding to two sector disappears in the non-supersymmetric case. You cannot use the same trick. So you're stuck at that singular point. So there's a holography in some singular sense, but not in the usual sense that we think. Yes?
Can you make this a sharp conjecture about CFTs? Like, would you say if there's a gap in
If this is true, but people have made the opposite statement, that if there are CFTs with gap, then you can reconstruct the ADS. Polchinski and company had this argument. So this would, if you take that into account, if that statement is correct, this would make a statement that CFTs with a huge gap cannot be non-supersymmetric.
How big a gap does it have?
This relates to ADS scale. So there's a parametric scale. So for example, for the 2D theory with the central charge, so you take C large. Take, for example, to be concrete, 2D CFTs with C large, the gaps which are bigger than C. That's a very concrete case. Cannot be that big a gap. Yes, that there's nothing that's depleted until C. Sorry?
A lot of examples of holography, the gap is smaller than C.
Supersymmetric ones for sure. So I'm just saying that you can have no. So let's think. So when you take a vev, when you give a vev to the fields, for example, symmetric products of K3, you give a vev precisely to get rid of these gapless modes. So you get rid of these gapless modes. But the same thing cannot be done in the non-supersymmetric case. So how are we doing with time?
12:18.
Okay, good. So we are up to conjecture 10. Okay, before I say conjecture 10. So So what do we know in string theory? So we know that ADS vacua for supersymmetric one so for supersymmetric ones, we know ADS vacua and Minkowski vacua exist. So lambda less than 0 or lambda equal to 0 are stable situations. Now, how about non-supersymmetric ones? Well, first of all, lambda positive cannot be supersymmetric. So this cannot be supersymmetric, but we can talk about no supersymmetry. And we can ask, what about lambda less than 0 or bigger than 0? What do we know about these cases? Well, if this conjecture 9 is correct, that means that the ADS case, you can have, but they cannot be stable. They cannot be stable ones. So for lambda positive, non-supersymmetric one, the least conjecture we can have is the sitter is not stable. That's the most natural one. It's consistent with what we think string theory does. I don't think any string theory objects to that. I think almost all string theorists believe that the sitter, even if it exists, is at best metastable. So we believe that in some sense there are no non-supersymmetric stable situations. At least that's the belief. Nobody has managed to construct anything which is perfectly stable, which is not supersymmetric one. So the only stable things in string theory or quantum gravity are supersymmetric ones. If that's the case, that is why supersymmetry is interesting. Supersymmetry and gravity go hands in hand in the sense of stability. Anything else is going to be transient. It's going to be metastable or not stable at all. So, sorry?
What about flat non-supersymmetric?
The what?
Minkowski.
You can have, right? Supersymmetric ones you can have. We don't have any examples. So every example we have that we have understood is that people conjecture that there's metastable or not stable. Now, the constructions, so people have constructions for de Sitter, at least I would say proposals for de Sitter constructions. And this is going to be the subject of my next week's talk. What do we say about de Sitter more precisely in the non-supersymmetric case? Is it metastable or not stable at all? That's the question. And so the least conjecture is that it's not stable, metastable. Well, it's not stable one way or the other. And a stronger conjecture is not even metastable. So that requires a lot of discussion, and people are still debating it and so forth. And I will postpone that discussion to next week when I talk about more broadly. So next week's discussion is not just going to be about the conjecture about de Sitter, but more generally, string theory and cosmology. Basically, what string theory can do in the context of cosmology, or what may it not be able to do because of Swampland. And I think I will stop here, and I will let you ask questions if you have some. Thank you.
Just a comment. I mean, a lot of your arguments are use geometrical logic, but I don't see how non-geometrical strings would fit in your picture.
Well, first of all, as I said, the arguments are not supposed to give you proof. The argument is supposed to give you indicative. So I take the easiest example, not the hardest example. We can also do the non-geometric ones, and we are familiar with non-geometric ones, and there are no counter examples in that context either.
Well, I mean, a lot of your arguments use geometric, like having a circle and so forth. And maybe if you have a non-geometrical object, then you don't have a circle. And so comment, but
no, it's a good comment. But I would encourage you, if you believe any of these conjectures can be proved false by non-geometric ones, we do have non-geometric constructions in string theory, like asymmetric orbifolds. I don't know if you call them geometric or not, but you can try to use them.
Exactly. I mean,
you can try to use them to disprove them. If I want to illustrate the principle, I won't use a complicated example to illustrate it clearly. I'll use the simplest example. It doesn't mean I could not have done an asymmetric orbifold version of the same thing.
I mean, you could. Okay. I mean, you can. It's an area for investigation. Let's say.
Well, you can investigate it. I don't think you will find something which is because of that, but you can certainly investigate it.
And the other is how do little strings fit in this picture?
Little string is like field theory in higher dimensions.
No gravity.
It's just no gravity.
No gravity, but
yeah.
still it's a string theory.
Yeah.
Right?
No. You can call it string theory. That's fine. It has some string objects. That's true. But it's not gravity. So I didn't say every string theory is gravity. Six-dimensional theory is little string theory, or even the non-little string ones have string excitations. So we know that 5D and 6D conformal theories involve when you go away from the conformal point by giving VF to expected fields, it gives you some very light strings. So having strings is the hallmark of interesting conformal system in 5 and 6 dimensions. Yeah, but there's no gravity. I did not claim that extended object means gravity. I said the opposite. That if you have a quantum gravity, it must be extended object. That's different.
Actually, in that sense, since little string came to discussion,
Can't hear them. Let me ask.
in that sense, since little string came to discussion, this argument on compactification on the radius and then discovering that there are extended objects.
I can't hear you.
The extended objects
Yes.
that you
Yes,
you
yes.
explained that should be there when you have a gravity theory and
Yes,
you
yes.
compactify.
Yes.
In case of little strings, that would mean that there are no extended objects if I compactify on a circle.
Well, in
or-
fact, little strings when it has T duality.
Yes, yes, yes.
It
That's
does
what-
have.
That's exactly
It
what
has
I'm
similar
saying. There is
properties.
no gravity. So what I'm saying is that the argument was that if theory is gravitational, we compactify on a radius r, right? And
You have
then
light
we argue,
objects.
and then we will discover that.
That's an example. So the
but
light
in little
string.
strings it happens without gravity.
Well, I didn't say that the only way it
Yeah,
could happen
I-
is with gravity. It's
that's
the
just
opposite.
comment.
If you have quantum gravity,
Yeah,
you
yeah.
have to have extended
Yeah,
objects.
that was just comment. So I had another question actually, which is, we want to break supersymmetry at some point, so we have to have supersymmetry breaking.
Yes.
But then you would argue that it will be not stable
Yes.
because there is no
Yes.
supersymmetry.
Yes.
So somehow there is a conflict. We
No.
want to break supersymmetry.
No, you can have like rolling quintessence speeds.
That would be stable.
No, it's rolling.
Do we want that as a?
That's the subject of next week.
Sorry.
Some people like it, some people don't. I don't know. We'll talk about it.
You mentioned that 2D gravity was often the exception to the rule,
Yes.
and you mentioned this in the case of global symmetries.
Yes.
Are there other examples of conjectures?
Well, for example, these bounds we got for the again next week when we talk about v prime over v bounds, there's typically a denominator d minus 2.
I see.
So
Okay.
there two dimensions are special, and gravity is boring in 2D, so it's kind of.
I mean, gravity is also pretty boring in 3D, but nonetheless it all.
I always try to be conservative, say 4 and higher, but yes, sometimes 3 is the borderline. Sometimes worry, but things seem to work more or less in 3D. But
2 and 10 are very special. There are two numbers, 2 and 10.
One other question.
Yes.
The distance, and you may have mentioned this already, so I apologize if you did. The distance conjectures. What goes wrong if they aren't satisfied? Do you have examples?
Sorry, just a second. let me just hear.
What goes wrong if the distance conjectures are not satisfied? Are there some things that go bad?
No, nothing goes bad.
Okay.
I mean, sorry. Something should go bad, but not that I know why, a priori. For example, I could imagine quantum gravity or something in supersymmetric one with no extended object would circle. What's the problem? Go down. Should have been okay, but somehow it's not okay.
So it's not known.
It's not known, but it
should-
seems like
should
all
be
the
there.
examples we have is like that. It's just, as I said, the questions of why, I'd love to be able to say, yeah, I give you a proof, but we don't have it. We just have examples. Of course, sorry?
There is a simple argument that I made in favor that
Okay, go ahead. Yeah, you can give the speaker to him.
if you have a massless scalar, then it's also a force. And if you require that the gravity should be the weakest force, that means there should be some particle such that it couples to the scalar stronger than it does to gravity. And the coupling of the particle to the scalar is the derivative of the mass of the particle with respect to the scalar. So just think of a Yukawa coupling or something like this. So this tells you that the derivative of the mass of the scalar should be bigger than the mass of the scalar. That's the analog of the g bigger than m, but for scalar force rather than gravity force. And that's the equation for an exponential. So if you didn't have a scalar becoming exponentially light, when you some particle becoming exponentially light, when you move along the scalar field space, gravity will stop being the weakest force. Yeah, so that's just an argument you can make.
Any other questions? Let's thank the speaker.